In this video, I wanted to take a little bit of time to discuss in a little more detail what the gradient actually is, and also kind of compare that to the directional derivative and give a little bit more intuition behind how all of that fits together. So first and foremost, I mean, all of this is based on what the gradient, frankly, well, actually is. So let's start there. So what is the gradient? Well, if we have a function f of x, y, then the gradient, which is denoted by this upside down triangle, a nabla, whatever you want to call it, of a function f, x, y, that's a vector. So I really want to stress that it's a vector, that its components are made up by the partial derivatives of the function that you're working with. The example that I have here, I'm just working with two variables, but I do want to point out that this does generalize quite nicely to working in higher and higher dimensions by just simply adding on more and more components for each variable that you're working with. And but anyway, just so we know what this looks like, if we have f of x, y is equal to, say, x squared plus y squared, then our gradient of this function at a point xy is equal to 2x 2y, okay? Because this is our partial derivative with respect to x and our partial derivative with respect to y for that function right there. Okay, well, I mean, that's all very well and good. We've gone through and done this computation, but what does this actually tell us? And I mean, I'm saying, okay, gradient at a point xy, what does that actually mean? Well, like I said, this is a vector. And it tells us how the function is changing at that specific point. And I mean, maybe you could have kind of picked up on that just from the fact that we're working with the gradients, or with the partial derivatives with respect to x and y, which tell us how the function is changing in the x direction, how the function is changing in the y direction, and we put them together and we get some notion of the direction that the function is changing in. Great. So it's a vector that tells us how much f of xy is changing at a specific point. So what exactly kind of information do we get about how much this thing is changing? Well, first of all, it is a vector, so it points in a direction and it has a magnitude. Well, the direction that it points in is actually the same direction as the direction that the function is increasing the greatest. And what does that mean? Well, it really just means to say, how can we best change x and y in such a way that we maximize the increase, the resulting increase in f? So the direction that x and y should be changed, basically. Okay, well, I mean, it's a vector, so we've taken care of the idea of what the direction tells us. Well, the second piece of a vector is its magnitude, and what the magnitude of the gradient vector tells us is actually the rate of change in this direction here, the direction of greatest increase. And I just want to stress that this is the rate of change in this particular direction, because that's going to kind of come into play when we talk about the directional derivative here in a bit. When we're working in higher dimensions, unlike in working with, just like the standard f of x is equal to y, all of a sudden, when we start talking about the gradient and rate of change, we want to emphasize that it's the rate of change in a particular direction, okay? So anyway, let's work a more concrete example and kind of talk about what that looks like. So we're going to return to this example, f of xy is equal to x squared plus y squared. And we are going to find the gradient of f at the points 1, 2, and 0, 0, and let's actually do one more. Let's do 3, -2. Okay, so we found the gradient earlier. We said that that was equal to 2x, 2y. Okay, so all I got to do to find the gradient at a particular point is plug that point in. So for the point 1, 2, so you have the gradient at 1, 2. This is equal to the vector 2, 4. Okay, so I mean, that's all there is to that computation, but let's talk a little bit about what that means. What this tells us is that, first of all, this is moving in the 2, 4 direction. And typically when we say moving in this direction, we mean that you should really probably work with the normalized vector, or the unit vector associated with that. But anyway, moving in this direction for the xy values results in the greatest increase of f of xy. And so what I mean by that is just saying that instead of saying, so like we're starting at the point 1, 2, and if we move 2 units in the x direction and 4 units in the y direction, that's going to result in a greater change than, say, moving in the -3 direction in the x component, and then in the +7 in like the y component or something like that. Okay, so relative to all the other ways that we could change x and y components here, moving in this kind of general direction, but again, we can work with some sort of scaled version in this, and traditionally it's the unit version, will result in the greatest change in the overall function by plugging in that type of modified value of x and y. And the other piece of information is actually the rate of change in the 2, 4 direction. So rate of change of f in the 2, 4 direction is, and this is specifically at the point 1, 2, is given by the length of that vector, the norm or the magnitude or whatever other word that you want to use. And that's just equal to 2√5. Okay, so all that's saying is that the absolute fastest that the function can increase at this spot is in this particular direction, which a lot of times we'd work with the normalized version, which is 1/2√5 times that vector 2, 4. But moving in this direction results in the greatest change, and that particular rate of change is 2 times √5. So let's look at our next example, 0, 0. So if we look at 0, 0, our gradient at 0, 0 is just equal to, well, 0, 0. And I think it makes a little bit more sense to talk about the rate of change here first. Well, the rate of change is frankly 0, right? Because that's the norm of that vector. And we can kind of, this makes sense if you look at the picture instead of trying to think a little bit more like, just like, okay, how do I interpret this? So this is what our graph looks like. 0, 0 is right here at the base of it. Okay, and if we were to kind of like think about rate of change moving away from this spot right here, well, it's kind of the same idea as like, well, what if we had put like a tangent line or a tangent plane there? Well, it'd be horizontal. Okay, and horizontal means that the rate of change is going to be equal to 0. So it's not really changing anywhere there at the base. It's the minimum. That's just what happens. And we're not really increasing or decreasing anywhere. And that's exactly what this 0, 0 vector tells us. Okay. And we can kind of look at our third example, and it's actually going to be quite similar to what the first one that we looked at, the gradient of f at 3, -2. Well, that's just going to be equal to 6, -4. And what that means is that moving in the 6, -4 direction, or we can think more about the unit vector, which is, well, 1 over root of 36 plus 16, 1 over root 52, 6, -4. That's going to give the greatest increase in f. And its rate of change when we're going that direction is root 52. Okay, so that's kind of the idea behind the gradient. It tells you which direction the function is increasing the fastest in, and then it also tells you what the rate of change is in that particular direction. And this notion of rate of change in a particular direction kind of brings us to the idea of the directional derivative. So what about the directional derivative? Okay, so for this one right here, I really want to stress that first and foremost, the directional derivative is a number because it is the same idea as rate of change. So the directional derivative is a number, not a vector. Very, very important. This is not a vector. That tells you the rate of change of a function f of x, y. And again, this can be generalized to however many dimensions it is that you're working in a given direction. And if you kind of look back at my other video about gradients and directional derivative, you'll kind of recall that this is given at a particular point x, y, and that's equal to the vector or the direction that you're interested in dotted with the gradient of our function f at the point x, y. And I really want to point out that since we only care about the given direction and we're not concerned about the magnitude, this guy right here should always be a unit vector. Okay. So let's work a couple of examples, and then I want to kind of build up some of the intuition behind this and ground it back into some of the things we've already talked about. But key thing here, number, rate of change. Okay, those two are tied together. So for example that we're going to work with today, we're going to find the directional derivative of a function. We'll just reuse the same one that we had earlier, f of x, y equal to x squared plus y squared in the direction of the point, or in the direction of the vectors 1, 2, 1, 0, and 0, 1. Okay, so we had said earlier, first and foremost, that we just always got to compute the gradients, and that is going to be equal to 2x, 2y. And for our first example here, our vector that we want to work with, so this is E dotted with F. This needs to be a unit vector, so we're going to say that E is equal to the norm of this guy right here. or this divided by the norm of that. So it'll be 1 over root 5, because that's the norm of this vector here, times 1, 2. Okay, and then I'm going to take this and dot it with my gradient. So this is going to be equal to 1 over root 5, which I just kind of like to leave on the outside there. And then parentheses, it's no longer going to be a vector because I'm adding everything together. I'm going to have 2x plus 2y. If I were to plug a point in, this would give me a number of the rate of change of f in the direction of 1, 2. Okay. So if this were we can say that this is at the point, we can say 3, negative 2, kind of like what we worked with earlier. The directional derivative of f at 3, negative 2 is equal to 1 over root 5 times 6 minus 4. So 2 over root 5 is what that would be. Okay, so what that's saying there, though, because the directional derivative is the rate of change of f in a particular direction at that point, it's just saying that f changes by 2 over root 5 when we move in that direction at the point 3, negative 2. So if we look at b here, we're working with the vector 1, 0, and in this case, our e is, well, the length of that is 1. Okay. So this is going to be 1, 0 dotted with the vector 2x, 2y. Well, that's just going to give me 2x. Okay. And if I evaluate at, say, the point 3, negative 2, then we have 6. Okay. Well, kind of remember back to our what our gradient looked like. 2x, that's just going to be our partial derivative with respect to x. Okay, let me keep that in the back of your mind there. That just gave us the partial derivative with respect to x, because that's the only piece we kept around. We didn't scale it or anything like that. We completely locked off the partial derivative with respect to y. Okay, so let's look at c here. This time, the vector that we're working with is 0, 1. So then our directional derivative is going to be 0, 1 dotted with 2x, 2y. Well, in this case, I only had 2y left over. And that was just my partial derivative with respect to y. Okay. And if we do this at the point 3, negative 2, well, it's just going to give us negative 4. Okay. And if we kind of remember back to working with our gradient example earlier, well, this is exactly the same as what we had gotten for our x and y components in our gradient. Okay. So why do we care about this? Well, I show you these examples here to kind of encourage you to take a step back and try to tie these back into what we already know about our function, our partial derivative with respect to x and our partial derivative with respect to y. And the way that I like to think about the directional derivative just kind of intuitively is as using combinations of the partial derivative with respect to x and the partial derivative with respect to y to kind of generalize our notion of rate of change in a particular direction. So that way you're not just stuck working in the direction of x or in the direction of y. So we recall that fx gives rate of change of f in the direction of x, which in our previous example, that's just the vector 1, 0. Okay. And we also recall that fy is the same idea, but in the y direction. And we kind of saw in our last example, this popped up when we worked with 0, 1. That's just our y direction, okay? Well, suppose we want to know rate of change in some other direction, okay? Well, gradient of f, the absolute value of the gradient of f, or the norm of the gradient of f, gives rate of change in direction of greatest increase. And then the directional derivative generalizes all of this using combinations of fx and fy through the dot product to give the rate of change in any direction. So that way you're not just stuck working with, okay, well, what do I want to know about f with respect to x or f with respect to y? Now we can know by computing the gradient first, okay? So we always ground ourselves with these partial derivatives, fx and fy, but then we're able to take various combinations of them through the dot product to give the actual rate of change, which is a number. These are all numbers. Anyway, rate of change with respect to this particular direction, whatever direction you may want that to be. And as I showed in the last example, we can even use these particular vectors that point only in the x direction or only in the y direction to just simply go back to that rate of change in either x or y if we wanted to, but we don't have to. So anyway, I kind of hope that this has helped make things a little bit more clear about working with gradient versus directional derivative versus partial derivatives and what they all mean in relation to each other. So for some more complicated examples on the directional derivative, I do have a previous video that kind of goes into a little bit more detail of computing more difficult versions of that. So if you want to see more with that, I recommend that you check that out. But otherwise, I will see you later.